Now in this session, we continue with the points relating to Biot and Savart law. Now, just now we found that Biot and Savart law determines the very small field strength dV as mu 0 by 4 pi into IDL sin theta by r square. This is the formula. And the figure we found that there is a length element dl and a current I flowing through it, and there is an angle we define with respect to the point x. This is the figure we consider. Now here in this case, suppose we consider the point x lies somewhere here or somewhere here. Means I consider the point x either here or here. I mean, it is falling on the line that is passing through the length element dl, right? The direction of flow of current. If the point lies here or here, the value of theta is found to be either 0 or 180 degree. That means that sin theta is coming here. So sin 0 is 0, sin 180 is 0. That means that for those points falling on this line of flow of current, wherever it is, the strength of the field will be 0. And that is applicable to what? As you consider this line, that is falling on this length element also. So suppose you consider the point on the length element, there also the magnetic field strength will be 0. So actually this magnetic field effect is produced around the current carrying conductor, not on the current carrying conductor. That's a very important point to be noted. So as the current flows, there is a magnetic field produced around the current carrying conductor. Okay. Now, if the field is produced around the current carrying conductor, then there is a problem. What is the direction of flow of current? Sorry, what is the direction of the magnetic field? Because magnetic field is a vector quantity, so you must be having a magnitude and a direction at every point. So, to determine the direction of the magnetic field around it, there are many rules we consider. So let us consider the simple one, that is thumb rule, right hand thumb rule. Now suppose this is the current carrying conductor, or let us see the case. Suppose this is the current carrying conductor, and suppose the current is flowing along this way, that is along the direction of the top. Then as the current flows along this direction, I hold the conductor in my right hand palm like this, such that the thumb points along the direction of flow of current. Thumb is pointing along the direction of flow of current. Then the direction in which other fingers curl around, that is like this. That direction is the direction of the magnetic field around it. This is what the thumb rule says. Direction of flow of current. Thumb shows the direction of flow of current, holding the conductor in this way. So, direction in which the other fingers curl around, that gives the direction of flow, direction of the magnetic field around it. So, even though the magnetic field is actually a circular loop around it, you can determine the direction of the field at every point. Now, to understand that, let us consider the current I flowing through this straight conductor in the upward direction. So you take the thumb rule here, holding it like this, and the finger curl around like this. Okay? So the magnetic field around the conductor will be going like this. Okay? Starting going like this. Alright? So at every point, suppose I take a point here, then there will be a tangent, no? This is the direction of the magnetic field. And at this particular point, if I take the tangent will be like this. So like that, all around you can have the direction. Now, suppose I consider the points lying on the plane of the ball, then that one will be one over here and one over here. Now, as the magnetic field goes like this, at this point, the direction of the magnetic field is towards you. Okay? The direction of the magnetic field is perpendicular to the plane of the board and towards you. And that is shown by a circle and a dot. This is very important representation of the direction of the field. A circle and a dot. At this point, the field is into the plane of the board, perpendicular and into the plane of the board. That is shown by a circle and a cross. Into the plane of the board, out of the plane of the board. Now what these two represents is actually this one. You will be representing a vector with an arrow. So this arrow will be having a head and a tail. So this is actually, you are seeing the head of the arrow as it is coming towards you. This is head of the arrow, that means coming towards you. This is tail of the arrow you are seeing, that means the arrow is going away from you or into the plane of the board here. So this is how we represent the direction of the magnetic field in our problems and all. So whenever you see a circle and a dot, it is the head of the arrow, and circle and a cross, this represents the tail of the arrow. Is that part clear? Okay. Now, let us see. We said that it's a vector. The magnetic field is a vector quantity. Then there will be always a question possible, that is, represent the Biot Savart law in the vector form. As we studied Coulomb's law in vector form, right? Here I am talking about the Biot Savart law in vector form. Now, the vector form of the Biot Savart law is given by mu0 by 4 pi into ideal cross R. So I am taking current element and the distance R as vectors. Ideal cross R by R cube. Ideal cross R by R cube. This is the vector form of Biot and Savart law. So, just by considering this ideal cross R, from this cross product you can find the direction of the magnetic field at that point. Because cross product of unit vectors and all you studied in 11th standard, you can follow that. Okay, so this is very, very important. So where all this field is existing and how the field is and how to determine the direction of the magnetic field and the vector form of magnetic field is all obtained from Biot and Savart law. So these are the basic things relating to Biot and Savart. Okay.